Swayam Prabha. Digital India. Educated India.
Okay, hello everyone. Let me introduce myself first. My name is Barry Leonard, and I am from National Taiwan University of Science and Technology, or Taiwan Tech for short. In today's talk, I'm going to introduce about the process simulation and control of cyclic distillation processes via Aspen Plus distillation. So my talk today is about the simulation of cyclic distillation process using Aspen Plus Dynamic Simulator. And my talk today, I will first try to introduce what kind of system is cyclic distillation, and how exactly are we able to simulate this kind of system using Aspen Dynamics Simulator, and our simulation results, and lastly our conclusion. So for the introduction, we know that distillation column technology is a very energy intensive technology, and it requires a lot of operating costs in form of energy. And so far, we have tried the process system engineering community have tried to do a lot process intensification, for example, to reduce the costs of using distillation column. And a breakthrough actually came in 1961 by Cannon et al. So Cannon and his team invented a system called control cyclic distillation, which can improve the cyclic distillation process. And basically, if we take this system way further, we can see the basic concept from the work introduced by Lewis in 1936. So actually, this system has been here for a long time. And if we take a look in Lewis' paper entitled The Rectification of Binary Mixtures, we can see that he introduced three types of distillation column. And here I'm going to just talk about these two types, the case 2 and case 3. So if we take a look at case 3, I think we are familiar that this is more or less just like the conventional distillation, where the liquid will flow down from stage to stage in a countercurrent manner. And if we take a look at case 2, there is a little bit of difference here with the liquid flow on the stage, which the liquid will flow on the same direction on each stage. But because of that, this kind of design will need this kind of pipe to make sure that the liquid will fall on the same side of the column. And interestingly, in Lewis' work, he mentioned that the case 2 actually have the best efficiency compared to case 3, and even compared to case 1, which is just a flash unit. And however, because of these difficulties in the column configuration, the work from Lewis was not picked up anymore. And in 1961, Cannon came up with the idea of controlled cyclic distillation, or we can also say a periodic distillation. So this is the first time this idea came up, but there are some issues regarding the hydrodynamics where the liquid, where if we use like sieve plate or bubble cap tray, the usual conventional trays, the liquid will mix between the adjacent stage. And there where the next invention came in. In 2011, Maleta et al. They invented a new kind of tray, specifically designed for cyclic distillation, called Maleta tray. And from then on, the cyclic distillation has been picked up, even by the industry, and to the industrial scale. Can see here the example is ethanol production and also for kerosene fractionation. So the aim of this work is to develop a rigorous simulation method that can accurately predict the dynamic behavior of cyclic distillation column. Because so far, there's been very few work that talk about the simulation of this column, and there is no like a direct solution. Even using Aspen plots, there is no model to be used to simulate the cyclic distillation. And there have been some work in the simulation part where they use mathematical model in MATLAB to simulate this kind of system. However, uh, the advantage of using Aspen Plus Dynamics is that we can actually observe a detailed information and the interaction within the cyclic distillation column. So I will try to introduce the cyclic distillation column. And so the basic principle of cyclic distillation column is that it makes the use of separate phase movement, or we actually separate the movement of vapor and the movement of liquid to two different periods within the column. And the key advantage of this kind of system is that we can have an increased separation efficiency, and we can also have a reduced energy requirements, reduced number of stage, and increased column capacity. So what is separate phase movement? Basically, we just separate the vapor flow and the liquid flow inside the distillation tower. So during the vapor flow period, and this is a time function, during the vapor flow period, the vapor will flow upward from the reboiler plate to plate, while the liquid will remain stationary on each plate, something like this. And in this period, the energy and mass balance, the energy and mass transfer will occur. And the consequence period will be the liquid flow period, where the vapor flow from the reboiler will be stopped, and the liquid will be allowed to flow down from this one stage to the other stage. And usually we assume that there is no energy and mass transfer occur during this period. So back to the Lewis, these are the three cases that Lewis introduced back in 1936. And the first case is actually a single tray, which we can just assume a flash tank. And it has a ratio between the overall Murphy efficiency to the point Murphy efficiency of 1.72. And case 3 here, which is just the conventional distillation, has the efficiency ratio of 1.5. Interestingly, for the case 2, which is pretty much similar with cyclic distillation, can have the efficiency ratio of 2, which is the highest among all three. And we can see here that for the case 2, because we have like same liquid flow direction on each stage, we can have this parallel concentration gradient within the column. Well, for case 3, for the conventional distillation, we cannot have the parallel, and we actually have the anti-parallel concentration gradient. And so the cyclic distillation substitutes this space axis of concentration space plot with the time dimension. So basically, using this kind of method, we transform the position axis here with the time axis, and we can have the parallel concentration gradient along the time during the vapor flow period. So this is just more detailed into what Maleta tray is. So this tray is specifically designed for cyclic distillation, and this tray was actually designed to just overcome the hydrodynamic problem where the liquid from one tray will mix with the other tray during the flow. And using this type of tray, we have the main chamber here, up here, where the liquid will be retained during the vapor flow, and the vapor liquid separation will occur. And the chamber is called the sluice chamber, where it just acts as a temporary liquid storage during the liquid flow period. So during the VFB, the liquid retained up here, and during the LFB, the liquid will be retained down here, like that. And so for our methodology to simulate this kind of system, we use flash unit to represent each chamber on each stage. So we can see one single red rectangle here represents one stage. So one stage will have one main chamber and one sluice chamber. And so the main chamber, as I explained before, is the vapor liquid mass transfer area where the mass and energy transfer occur, where the liquid will be retained during the vapor flow period. And the buff or buffer, or we can also say sluice chamber, is just the liquid temporary storage area. So it just temporarily store the liquid during the liquid flow period. And this is our operation strategy. So during the VFP, uh, the, li the liquid outflow from the main chamber will be stopped. The red line represents that it's closed. So the liquid will be retained on the main stage, and the vapor will go up from one stage to the other stage automatically, or we set the control in auto so that the stage pressure will control how much flow the vapor will be. And the liquid outflow from the sluice chamber will be open to let the liquid from the stage N flow down to the stage N+1. And we can also see that the feed is open during VFP. And then during the LFP, the feed will be closed. Actually, the vapor flow from the reboiler will be closed, but we still set the vapor flow on each stage to be auto. And the liquid flow from the main chamber will be open to let the liquid flow down to the buffer, and the liquid from the buffer will be stopped. So for the column scale strategy, it's pretty similar actually. So during the VFP, the vapor will be allowed to flow from the reboiler up to the column to the condenser, and the feed will be open, the distillate and the bottom will flow out. And during the liquid flow period, basically almost all of the liquid flow will be stopped, and there will be no feed, there will be no distillate, and there will be no bottom. However, we try to maintain the feed and product throughput for the system, so there will be some adjustments in the feed flow rate, something like that. And so in this system, we will have pressure controllers to control the main chamber and sluice chamber for each stage. Of course, this is actually just a virtual control of the simulation and not actually there in the real plant. And we also have a pressure control for the condenser, and for the reboiler, we use pressure control to control the vapor flow rate. And for inventory control, we have the stage level control, reflux drum, and reboiler level control. And for quality control, we have the temperature control. So I think this kind of control scheme is pretty common for distillation column. And for the simulation result, we chose the ethanol propanol separation system as our base case. So here we use the Wilson property method, and this is our binary parameters, and this is our TXY diagram for ethanol and propanol, and this is the temperature profile, and this is the temperature sensitivity profile. And as we can see that stage 16 here is the most temperature sensitive, so we choose this stage as the temperature control stage for the quality control. And for our distillation, we will have 21 stage total, and our feed will be 100 kilomole per hour with 50 kilomole of ethanol and 50 kilomole of propanol. And our reportability is 2.8 gigacalorie per hour for the conventional distillation. So with cyclic distillation, we actually have two additional variables. We call it VFP and LFP, which is just the time, how long the vapor flow period and the liquid flow period would be. But the determination of these two parameters are actually very important. And the VFV has to be long enough to let the vapor liquid equilibrium to be reached on its stage or for the separation to happen. Or in the case for reactive cycle distillation, we also need the VFV to be long enough to let the reaction occur and reach its equilibrium. And for the liquid flow barrier, it's relatively more simple. We just need it to be long enough to allow the stage drainage. And here we can see the results over several hundreds of cycles. And we can see that after around 300 cycles, the system will reach the pseudo steady state. And if we zoom in, this is how the system actually looks after it reaches the pseudo steady state. So we can see the temperature of reboiler and pressure of reboiler oscillates. We can also see that the feed actually oscillates. So this is here is during the VFP, we charge in the feed, and then during LFP, we stop the feed and so forth. And we can also see the stage pressure oscillations here. So because of the nature of cyclic distillation, this system naturally cannot reach a true steady state, but it can only reach a pseudo steady state. And this is our simulation results. So comparing the conventional distillation and cyclic distillation, we can save a lot of energy, and we can actually save almost 50% of energy just by changing from conventional distillation to cyclic distillation with the same number of trays, the same column diameter, and the same feed location and flow rate. And we also do some disturbance tests. We do plus minus 10% throughput disturbance and plus minus 5% feed composition disturbance. And here we can see that the red dashed line represents the conventional distillation and the solid blue line represents the cyclic distillation. And we can see that after around 3 hours, the cyclic distillation can reach the pseudo steady state. So it's not too bad, even though it still takes a little bit more time compared to the conventional counterpart. And here is the minus 10% throughput disturbance. We can also see that the cyclic distillation can retain the target purity quite well. And here I just want to point out that the purity of the conventional distillation is way higher than the purity for the cyclic distillation. And this is for the plus 5% feed composition and for minus 5% feed composition disturbance. So in conclusion, this work provides a new approach to simulate more rigorous cyclic distillation that allows for detailed observation on the column behavior, including the prediction for interaction between the liquid hold diamond pressure and dynamic flow rate, and also pressure drop. The cyclic distillation process for ethanol propanol has been successfully simulated using the flash module in Aspen Post Dynamics, and the product purity of 99.5% is reached, and the cyclic distillation can save energy consumption to almost 50%, which is huge. And the performance control of the system was tested through several disturbance, through the 10% feed disturbance and 5% feed composition disturbance, and the cyclic distillation has been shown to be able to reach the pseudo steady state back within 3 hours with a low number of error, and it shows that the cyclic distillation can have a good controllability and disturbance rejection ability. So that's all for my talk today. Thank you very much for your attention.
Yeah, thank you, Mr. Barry Leonard. Any questions? Yeah, we have one question from the live audience.
Okay.
Hello, myself Bandakiran. Very nice presentation. That first time I'm hearing this cyclic distillation. I also done my work for my PhD on the heat indication of distillation column. I have a few doubts related to that. You said that it's a pseudo steady state, right?
Yes.
Yeah, like
yes.
how much percentage is the variation of that saturation efficiency?
I'm sorry, I didn't catch that.
So like the variation, like pseudo steady state means you won't get the same concentration, same purity all the time, right?
Oh, yes. So
what's the variation percentage?
So basically, because it's a cyclic distillation, it cannot reach a true steady state. So we can actually reach a pseudo steady state where each parameter is repeated every cycle. And for the concentration, it's actually pretty stable, but if we look closer, it actually still oscillates. And for the validation of this kind of system, it is quite difficult to get the real plant data to validate. However, we did a validation on several other simulation that was done using mathematical model using MATLAB. But in my opinion, the other experiments that was done, the other papers that have been published also said that the pseudo steady state will be reached and not a true steady state.
Okay. And have you not done any technical economic analysis?
I'm sorry?
Have you done the economic analysis for this study?
For the economical analysis, we have not reached that part yet. So our goal here is to minimize either the stage number or the heat, the energy reduction. But we haven't reached to calculate the TAC, total annual cost yet.
Okay. Does it vary that the dimensions of that column with the conventional one?
So for the dimension of the column, we managed to make sure that the dimension is actually equal in terms of the diameter and the column height. As you can see here, the tri height and the diameter is not shown here, but the diameter is also the same.
Okay. Thank you.
I don't think so there are any online questions. Thank you, Mr. Barry Leonard, for your presentation
Okay.
and interesting work.
Thank you very much.
Have a nice day.
Thank you very much.
Yeah. And